Oh, good. Thank you. Thank you very much for the invitation. It's a pleasure to be here. Now, I know I'm standing between you and dinner. It's not a good spot, right? But bear with me. I have actually some cool results to show you. So the paper in one page, primer on perpetual futures. If you're like me, you never heard about this before. This is the way to learn. It's very clear, very honest. This is not some crypto bro trying to sell you something. This is very informative. There is one theoretical result and one empirical result. The theoretical result is this one. In the absence of random maturity arbitrage, when the risk-free rate is constant, and when the difference between the perpetual future rate and the spot is always bounded, then the perpetual future rate satisfies this equation. What's the empirical evidence? They showed you a strategy where you can actually make money when those bounds are no longer satisfied. As Asaf said, you make money mostly into 2020, 2021, less so in the last year. So what am I going to do in this discussion? I'm going to go back to the basics. I'm not going to go for the random maturity arbitrage. I'm going to go back to really basic. What's an arbitrage? The textbook. So I'll start with a little bit of theoretical background, if you want, and then I'll go to the data. I learned a lot from this paper and a bunch of papers that are referenced in Asaf's paper. I also learned a lot from reading those two papers. I'll explain that in a few minutes. So let's start the way Asaf did, by thinking about just a simple forward or future contract, let's say 1 month. So I can define a stochastic discount factor that's going to be useful for later. I can define an exchange rate. Let's think about the spot exchange rate in US dollars per unit of cryptocurrency. So it could be a Bitcoin, could be something else if you want. If S goes up, the value of a Bitcoin appreciates. I'm going to assume that there is a 1 month forward contract, something that you sign now. It's going to happen 1 month later. And it's also going to help me to think that there exists a gross risk-free rate in US dollars. That's relatively okay. I'm also going to assume that there is a gross risk-free rate in cryptocurrency. That we can discuss, but for now, let's take it as an assumption. Now, I want you to think about a series of excess returns. I have 3 excess returns. Here's my third one. I'm going to borrow S dollars, just the amount of money I need to buy my Bitcoin. I borrow my S dollars for 1 month. What do I do with my dollars? I buy 1 Bitcoin. What do I do with my Bitcoin or another cryptocurrency? I invest it. Let's assume I can do it without risk. At the end of the month, I'm going to get some cryptocurrencies. I don't want to take any exchange rate risk, so I'm going to sign a forward contract now that's going to convert those Bitcoins back into dollars. So what's the excess return? I'm going to have to pay back my debt at a risk rate in US dollars, and I'm going to make some money in Bitcoins that's going to be transferred in US dollars. As you see, everything is decided and known at date T. There is no risk. You can forget the stochastic discount factor for now. And what you get is the ratio of the forward to the spot equals to the ratio of the 2 interest rates. That's CIP, cover interest rate parity. And there are some people who love looking at the deviation between the left-hand side and the right-hand side. It's a cool topic. Now, there's another way to think about excess return, and you don't hedge your currency risk. So what do? You borrow the same amount, S dollars, which is what you need to buy 1 unit of cryptocurrency. You invest for 1 month, and you wait and see. And what's going to be your return? Your return is going to depend on the value of the cryptocurrency in US dollars at the end of the month. So now what's, again, the excess return? You pay back your debt, so that's the risk rate in the US, the gross risk in the US, times the amount of money you borrowed. And how much do you get in Bitcoins? Well, it depends on the return on your Bitcoins, times the value of the Bitcoins at the end of the month. This is risk. This is not something you know at date T, at the start of your trading strategy. So you can play with that a little bit. By the way, this intermediary result is going to be useful for me in 2 slides. So okay, you can just denote it as a present value of future exchange rates if you want. The way we usually talk about this is in terms of risk premium. We think about what is the excess return. Well, it depends on how much money I make out of the exchange rates plus the interest rate difference. And we can write it as the usual covariance thing. Why do we usually spend a lot of time studying currency risk premium? Well, because I can play with the same equation, a little bit the way Sean did it this morning, and just iterate it forward. And the value of the exchange rate today is equal to what I expect the interest rate difference to be in the future and what I expect the risk premium to be in the future. So it's a way to think about the fundamental value of an exchange rate. Here it's just the exchange rate of dollars versus Bitcoins. Now with this, you have everything you need to think about perpetual futures without random maturity. So I'm going to think about buying this forward contract. I buy it now, and I sell it 1 period later. And I want to again think about what is the excess return. So I buy it at date t, I sell it at date t plus 1. But if I do this, as Asaf explained, I'm going to have to pay something that is proportional with this function kappa, this parameter kappa. I'm using the same notation as in the paper. And that's proportional to the gap between the infinite maturity contract on forward and the spot. This is, again, an excess return. There's no money exchange now. It has a price of 0. So you remember your law equation, E of MR equals 0, because R here is an excess return. So now it's interesting to have a stochastic discount factor. You remember I actually did not specify it, so it's going to be true for any discount factor. Now what I'm going to do is that I'm going to take this forward at date t that I know and take it off the equation, put it on the right-hand side. What you see now is that the price of this infinite maturity contract today depends on what I expect the price to be with the correct stochastic discount factor, and also the current spot, the current value of the Bitcoins. So I'm going to do the classic thing we do both on the stock market but also on the currency market. I'm going to iterate this forward. So you start with my previous equation. I'm going to write it again at date t plus 1. Once I have this ft plus 1, I plug it here. Simple math, right? And I get something like this. Now it's getting ugly. So here you have 2 ways to go. And this corresponds to the 2 papers that I mentioned earlier. First way to go, what we usually do in the term social literature, for example. You write a model for the stochastic discount factor. You specify a process for the SDF. You specify a process for the exchange rates, and then you solve your model. We can do that. I don't have time. So I'm not going to do that. Instead, I'm going to do what the second paper I mentioned does. I'm just going to make a strong assumption. But it turns out to be the same one that Asaf made. I'm going to assume that the risk-free rates are constant. Now, if the risk-free rates are constant, actually iterating forward becomes much easier. And I end up with something that looks like a transversality condition. We're going to have to discuss it. Plus something that looks like just a geometric series. So we can compute it. I'm going to assume for now that this term magically disappeared. We'll have to check that later. But for now, bear with me. It's not a crazy assumption. If this term disappears, you see what is the fundamental value of this infinite maturity contract. It's this thing. By the way, this is a special case of what Damien, Julien, and Urban derived. But here's what I'm going to do now. I'm going to specify kappa. I didn't tell you anything about kappa, so now I'm free to choose it, right? So I'm going to choose it. So I'm going to choose it so that it's exactly cancel out this term. You see, I'm cheating. I take the kappa equals to exactly this ratio of 2 interest rates. And what do we get? Well, the forward over the spot is equal to the ratio of the 2 interest rates. We're back to the CIP. That's cool, no? So now we have a basic way to think about this forward contract. I just assume that there exists as SDF. It's like assuming no arbitrage if you want. But I didn't have to introduce any random maturity. So now that we have this benchmark value, we can think back about, hey, what did I really need to derive this result? What are the assumptions I made? Because if there's any kind of deviation from this benchmark in a frictionless world, we'll talk about frictions later. In a frictionless world, it has to be that some of my assumptions are wrong. So what can be wrong? The transversality condition, you know, it doesn't look that bad. Think about it. E of M is just 1 of R, so it kind of cancels out. And as long as those gross returns are not negative, which is 1 plus the net, so it's kind of not crazy, this is actually going to look pretty good. I mean, you can check it in many models, but that's, I think, is going to hold. I think the key assumption I made is this, number 2. I assume constant risk-free rates in cryptocurrencies in dollars. Risk-free rate in dollars, okay, maybe treasury bill. Risk-free rate in cryptocurrencies? That's a little bit more difficult, right? And plus, here it has to be constant. So I think that's cool, because if we now study deviation from this CIP-like condition, it's like studying the interaction between a default risk premium, a term risk premium, and a currency risk premium. The interaction with 3 risk premia. And with Hanno and Andreas, we studied the interaction between 2, the term premium and the currency. It was already pretty complicated, but here it's going to be even more interesting, difficult. So I'm not going to do that in the rest of the discussion. In the rest of the discussion, I actually want to discuss my last assumption. You remember, I picked this kappa equals to the ratio of the 2 interest rates, so that the formula would look cool. So I'm going to discuss that, and I'm going to look at the data for that. So on the volume, I want to say that I'm very impressed with what Asaf and the quarters have done, because from reading the SEC and other players, it seems like not all the volume data can be really trustworthy. And they did the hard work of just only using the good sources. I'm not doing that here. I'm just showing you the aggregate. So yes, as I've said, it's a market of billions of dollars. And yes, it's just 2 orders of magnitude smaller than the usual currency market. So is it going to become as big? I don't know. I think there are reasons to read these papers, even if that market never takes off. I'll explain that in a second. Now, you can actually just Google this and find those contracts and look at the characteristics of those contracts. Here I'm just showing you a screenshot from my computer. The reason I want to show you this with those perpetual contracts is to explain why I didn't mention the bid-ask spreads. In the way I derived the formula, it would be extremely easy to add bid-ask spreads, right? Since we're talking about returns, just think about you're buying at one price and selling at the other one. So that would be easy. But it turns out that actually the bid-ask spreads is now pretty small on those markets. So maybe that's not the first issue. No, I think the key issue is the kappa, and that's actually hidden in these funding rates. So to understand this, I had to go back to the details of the contracts. It turns out that you can actually find this and see how they actually trade those things and how did they invent it. And this is what I found reading this. Lo and behold, how do they compute kappa is just the difference in 2 interest rates. Interest rate in the US, dollars, and the interest rates, pseudo interest rates in cryptocurrencies. So that's exactly what we would expect if we wanted to derive something that looks like the CIP condition. So that's pretty cool. So that part is nice. The thing is that in cryptocurrencies, things are complicated, at least for an outsider, and there are also other things that I don't fully understand. On top of this interest rate component, that I think I understand, there's a premium discount component, but I'm not sure exactly what it is. And there is also some kind of dampener and a few things that I think the authors should actually study. This is where the bodies are buried. But it's actually cool that we are something close to what makes sense, the benchmark we have. Now, if we think about the arbitrage, and now I leave the world of the frictionless, no arbitrage SDF. I'll take 1 minute for that. Think about what an arbitrager would do. You see the forward rate that is too high, relatively to the CIP condition. Well, what you want to do is that you want to short the perpetual and go along the spot. And you have to think about what could go wrong. And I think a lot of things could go wrong. First, theft. Think about the FTX. You think your money is there, your money is no longer there. So there's no way to do an arbitrage properly, right? Okay, that's an obvious one. There's a one that actually Asaf has in his paper. It's actually really cool. What could go wrong is that the forward rate rises just when you want to unwind your contract. And this doesn't happen with the classic 1-month forward rate. Why? Because with the classic 1-month forward rate, when we reach the end of the contract, then the forward rate is like the spot rate. It's a 1-second forward rate is the spot rate. So you know exactly where it's going to converge to. It's not the case here. It turns out that actually when FTX blew up, this is something that I learned from Asaf's graph, the forward rate blew up, just spiked, just on that market, not on everywhere else, which is like really a big limits to arbitrage. And the last one is the counterparty risk, and that's related to the fact that there is no convergence. If you know a little bit about how clearing or derivatives are traded, the way it works is that at the end, when the contract matures, you know what's going to be the value of that contract. And here, this doesn't exist. So the way counterparty risk is, I think it's worth another paper. Yeah, it's not obvious. Okay, I know that my time is up. Sorry, Adrien. I really enjoyed reading this paper. And here's the reason why you should read it, even if you're not interested in cryptocurrencies. This is an example where there is something new in cryptocurrencies that could be useful elsewhere. And that's, I think, the reason to read this paper. Now, I think risk-free rates are constant. We have actually a pretty cool benchmark way. It's like a CIP, if you want, again, in terms of the risk rates in the two countries, in Bitcoins and in dollars. And if you want to think about why you're making money using the strategy that Asaf showed on another strategy, I think these are the things to think about. Of course, you have the transaction cost and the rollover risk, but the most interesting ones are this one, the interaction between the turn, the default, and the currency risk premium. And of course, the credit risk. That's a very polite way to say it. I stop.